All right, only terms with the same index. Remember, index is that little number inside. So here there's a 3, here there's a 5. That's the index. If it's a root that has no number inside, what would the index be? It's 2, because it's a square root, right? Like we've been doing square roots for a long time, and you know what a square root is. So if you don't see the index there, that is a 2, a square root. So only terms with the same index and radicand can be added or subtracted. Add or subtract the number in front, and then simplify. So if you look at this first one, this one has a root 5, and this one doesn't have a root at all. So we can't add them together. So I'm going to write already simplified. All right, so this 2 root 5 plus root 2 is just 2 root 5 plus 2. It's like it's not anything different. All right, let's look at the next one. They both have square roots, but they have different radicands. That's the number underneath the square root. So again, already simplified. So these were not like terms. Not like terms. But let's look at the next one. 5 root 6 and 4 root 6. Do they have the same index? Good, same index. Do they have the same radicand, the number underneath the square root? Yeah. So they're like terms. So now we can combine them. When you combine them, think about adding them as if you were adding 5x plus 4x. What's 5x plus 4x? 9x, right. 5x plus 4x is 9x. When I add these together, I just get 9 root 6. Notice the root 6 doesn't change. I just add the coefficients. All right, the next one is weird because you can see clearly that 8 and 2 are different numbers. But I'm telling you that there is a way to add these. So how can I add these if they're not like terms yet? What could I do? There must be a way to make them like terms, right? Is there any way I can change one of those radicals so that they become like terms? Which one can I change, the root 8 or the root 2? The root 8 changes. So I'm going to make a factor tree. 4 times 2, 2 times 2 times 2. So root 8 is the same thing as square root of 2 to the 3. And remember that when we simplify a radical, we want to make the index the same as the exponent. So I can break that into square root of 2 squared times 2 to the 1. It's a little bit of review from last week. Square root of 2 squared is just 2. And 2 to the 1 stays underneath. So I get 2 root 2. So now 2 root 2 and root 2, those are like terms. So I'm going to actually cross both of these out, and I can say they can be like terms after I simplify. I'm going to change my root 8 to 2 root 2. So I have 2 root 2, and I have 1 root 2. Notice that instead of calling this just root 2, I called it 1 root 2 so that I kind of have that coefficient there to add. 2 root 2 plus 1 root 2 gives me how many root 2? Very good. Good morning, Nasir. All right. Questions so far? All right, so remember that I did tell you at the end of class we're going to be doing an exit ticket, and before we do the exit ticket, I'm going to want to do a couple problems in practice together. So I'm gonna save a few problems for the end. Give me 1 second, I'm gonna see which ones. All right, let's look at number 5. Do all 3 terms have the same index?
Yes.
Do all 3 terms have the same radicand?
Yes.
Remember, the radicand is what's underneath the root. So they all have 2x. They all have an index of 3. So I can combine them just by combining the coefficients. So this is a 5. This is a minus 2. What's this one? What's my... It's a... Yes, it's going to be a coefficient of 1. So 5 minus 2 plus 1. Combine those. Did you guys get 4?
Yeah.
Okay. So 4. And I still have cube root. And then 2x. Number 6. Do you have the same index? You have... The index is the little number inside the root. Do we have the same index? Well, this is a square root, right? That's a square root, and that's a square root. So I think we do have the same index. The radicand is the number underneath. Do we have the same radicand? No. Do you think that there might be a same radicand if we simplify? It's definitely worth trying, right? So we're going to do a factor tree for each one. 27, 9 times 3, 3 times 3, 12, 4 times 3, 2 times 2, and 75. 25 times 3, 5 times 5. Hi, good morning. All right, okay, so here, 27, we have square root of 3 to the 3. 12, we have square root of 2 squared times 3. And 75 is square root of 5 squared times 3. I'm going to zoom that a little bit, sorry. Questions so far? Okay. 3 to the third, I'm going to break that up more to 3 squared times 3 so that I can take that 3 out. This one, the 2 squared and the square root, those are inverses, and so I can take the 2 out. This one I can take which number out? The 5, right? And then over here, I'll be able to take this 3 out, and the other one will stay underneath. All right, now after simplifying, I do have like terms, so I can combine them. And remember, you combine them by combining the coefficient. So go ahead and do that, compare with the neighbor, and see if you get the same thing. All right, so 3 minus 2 is 1. 1 plus 5 is 6. Did you guys get 6 root 3? Good. I just combined the coefficients, the numbers in front. All right, number 7. Do they have the same index? The index is the 5, right? They all have 5. Do they have the same radicand? Not all of them, right? But you say kind of, because some of them do. So we'll combine the ones that we can. What can I combine with 2 fifth root of x? The negative 6 fifth root of x, right? So I'm going to combine this one with this one to get negative 4 fifth root of x. And then what can I combine with 7 fifth root y? Oh yeah, sorry. Oh, I froze it. That's my problem. There we go. All right, what can I combine with 7 fifth root of y? Do we have any other fifth root of y's? The 3, right? So I get 10 fifth root y. Okay? So sometimes you can't combine everything, but you can combine some things, and you should just do that. If there's anything that combines, do that. So remember, we're saving 8 till the end, and we're going to go to the back. All right, multiplying and dividing. So it says you can only multiply and divide radicals that have the same index, although just as a disclaimer, we did learn last class, or the class before that, we learned how to multiply when they had different indices. It's just that you have to change to fraction exponents, and we'll practice doing that. All right, so here you actually had a choice. You could simplify these first and then multiply, or you could multiply and then simplify. It doesn't matter. You need to do both things. So you just multiply the radicands, the inside parts, keep this as a cube root, and multiply 90 times 75, which I definitely can't do in my head, but maybe you can. 90 times 75. I get 6,750. Okay, so I have the cube root of this big number, and I want to do a factor tree for it. And here's the nice thing about the factor tree. The first step is easy, because I know two numbers that multiply to make this. I just found them right here. 90 times 75, right? So there's my factor tree. I'm starting it that way. You can then break it up any way you want. 90 can be 9 times 10, 3, 3, 2, 5. 75 could be 3 times 25, and then we have 5 times 5. All right, so all of those prime factors need to go into your radical. So I have cube root. I'll start with the 2's. I think I just have 1 2, right? Nope. Yeah, 25, and then that's a 2. So I have 2 to the 1. 1, 2, 3 threes, and 3 5s. Did I miss anything? You guys think I got it? Okay. So anything that's to the third power can cancel with the third root and come out. So on the outside, I have 3 times 5. On the inside, I have cube root 2. And of course, I can multiply 3 times 5. So my final answer is 15 cube root 2.
So why do you do 3 times
3 times 5 because they are both on the outside, and so you can combine them. Okay, number 10, they have different indices. So you cannot just multiply the 4x and the 4x when they have different indices. But what we can do is change them to fraction exponents. So remember that we had this example, x to the a root b like this. This is equal to x to the a over b exponent, like that. So here I can write this one as 4x to the 1/3. Remember, the 3 would be the denominator, times 4x to the 1/4, like this. So when you have different indices, then you want to change to fraction exponents. I think this problem ends up being a pretty long one. So let's just review multiplying exponential expressions with the same base. When you multiply, what do you do with the exponents? You add them, thank you. So I'm just going to use a little space on the side here to think through adding 1/3 plus 1/4. 1/3 plus 1/4, I need a common denominator. And so I can multiply this one by 4 over 4 and this one by 3 over 3. So I get 4/12 plus 3/12, which is 7/12. So I get 4x to the 7/12 because I added the exponents. And then I'm going to rewrite it as a radical. So when I rewrite it as a radical, the denominator becomes the index, and then the numerator is the exponent. So it's going to look like that. Oh. So we're just going to multiply these together. They have the same index, so nothing fancy happens. You can just say root 2 times root 3 is root what? 6. Root 2 times root 10? Square root of what number, guys? 20. Okay. The factors of 6 are 2 times what? 3. And neither of those repeats, so this does not simplify, but I think that root 20 will simplify, so I'm going to do a factor tree for root 20. All right, and since we have 2 2's, it will simplify. Okay, so 2 squared times 5, and that means the 2 can come out. So I have root 6 minus 2 root 5. Now notice the radicands are different, 6 and 5, so I can't subtract them, but I do have my simplified answer. I can't subtract them because this number is a 6 and this number is a 5. So for adding and subtracting, you have to have both the same index and the same number underneath the square root, the radicand. That was on the first page. We did mostly multiplying on this page. Okay. Number 15. A very common error is to just square each term, and that doesn't work because of the minus in between. But remember that squaring just means to multiply something by itself. So if you see something like this, don't be fooled. Don't try to square each term. Multiply it by itself like that. Okay, and then we're just going to distribute. Like we've done a problem like this millions of times over. Usually it has an x in it instead of a root, but we can definitely do this. I'm going to start with 4 times 4. So 4 times 4, I get 16. And then I'm going to do 4 times negative 2 root 3. Now you can multiply these together. The 4 will multiply times the negative 2 because it doesn't have a root on it, so it doesn't multiply by the root part. So that's going to make negative 8 root 3. Then I'm going to distribute the negative 2 root 3, this one here. So negative 2 root 3 times 4 is another negative 8 root 3. And then finally, I have to do negative 2 root 3 times negative 2 root 3. So there's like 3 parts to this problem, really. First of all, negative times negative is positive. 2 times 2 is 4. Root 3 times root 3 is the square root of 3 times 3? 9. But I know the square root of 9, right? Square root of 9 is just 3. So this can become 4 times 3 for this part. These two can combine. So negative 8 root 3 minus 8 root 3. You combine the coefficients. Negative 8 minus 8 is what? That's right, minus 16. So that makes minus 16 root 3. And then that 16 comes down. So this one comes down. Those two combine to give you this. And then this one becomes 4 times 3. 4 times 3 is 12. So I have 16 minus 16 root 3 plus 12. And then finally I can add 12 and 16 to get 28. All right, questions? All right, so root 11 times root 11, square root of 121. And then root 11 times negative 5. The negative 5 doesn't have a root on it, so it just gives you negative 5 root 11. Like, you don't actually multiply those numbers. Then I'll distribute the 5, so 5 times root 11 is plus 5 root 11. And then 5 times negative 5 is minus 25. What happens with those middle terms? They do cancel out. I love it when that happens. Negative 5 root 11 and positive 5 root 11 cancel out. Square root of 121 is 11. So I have 11 minus 25, and so my final answer is just negative 14. All right, so notice that word over there, conjugates. Without looking it up, talk to your group about what conjugates might mean, because that problem is definitely specialer than problem 15 or 14. Number 12 is a problem where we have to rationalize the denominator. So anytime you have a square root in your denominator, you're going to do times square root 8x over square root 8x, like that. And the reason we do that is because that squares your denominator, which will eliminate the square root. So I have 14 root 8x over square root of 8x squared. And that's how your square root cancels in the denominator. So I have 14 root 8x over 8. Now, in some problems, we're done there, but this one we're not. There's a few things going on. First of all, 14 over 8 would simplify, but before I even worry about that, I'm going to try to simplify the square root of 8x. Now, x itself is going to be stuck under there. Oh, I forgot my 8x. You guys didn't even tell me. This x is going to be stuck underneath the root, but the 8, that one can simplify. And if you do your factor tree, you have 4 times 2, 2 times 2. So this is either 2 to the third, or you can think of it of 2 squared times 2 to the 1. 2 squared and 2 to the 1. And the reason I broke it up like that is because it's a square root, so I want a squared. All right, so let's bring this down. I have 14 square root. I'm going to write my 2 to the third as 2 squared times 2 to the 1. I still have an x underneath the root.
Wait, why do you want to do 2 squared times 2 to the 1?
Because my root is a square root. The index of the square root is 2. That will cancel out with a squared, okay? If it was a cube root, I would want to break it into cubes. And then I still have 8x in my denominator. The 2 that's squared, that one can cancel out with square root, and that can get out of that root. So that's going to make a 2 on the outside. So I have 14 times 2, square root 2x, over 8x.
Could you also do the 7 times 2 square root 2x over 8?
Oh yeah, because you guys had already simplified. Yeah, I hadn't done that yet, but yes, that's what you would do. All right, 28 root 2x over 8x. Because 14 times 2 is 28.
And then you say,
And I'm going to simplify the 28 over 8. Guys, don't be confused about that, because I can simplify those two because neither of them is in a root. I cannot simplify the x over x because this one is a square root of x and this is a regular x. But 28 over 8 I can simplify. I can divide them both by 4 and get 7 over 2.
do you, wait, the 2x multiplied?
So I still have 7 root 2x over 2x as my final answer. That's a lot of steps. You guys got the important ones at the beginning. There are just some simplifying steps at the end.
Wait, when you do one,
Does anybody have a question or just want to hear a little recap of that problem? You want the recap? Okay. Guys, you do a really good job helping each other, but can you just give me a minute so I can do this recap, and then after that you can help each other again? First step, whatever root is in the denominator, multiply by that in both numerator and denominator. So you get 14 root 8x, and then root 8x times root 8x is root 8x squared. The square root and the square cancel, so you just have 8x in the denominator. Then we have to simplify the square root of 8x. So 8 can get a factor tree. It's 2 times 2 times 2, which is 2 to the third. But you can break your 2 to the third up into 2 squared times 2 to the 1. And the reason you want to do that is because it's a square root. If it were a cube root, I would stick with the 2 to the 3. So then I broke my 8 to be 2 squared times 2. That's here. Everything else is the same. The square root of 2 squared is 2, that comes out, and 14 times 2 is 28. Then I simplify 28 over 8 by dividing them both by 4. That's their greatest common factor. So 28 divided by 4 is 7, and 8 divided by 4 is 2. Questions on that one? Okay, in a minute I'm going to go back and we're going to work on 8 on the front, and then we'll do 11 and 13, and then we'll do our exit ticket. All right, number 8. They are not like terms yet, so far I'm thinking I can't add them, but I can simplify the cube root of 8. I just made a factor tree for 8, so this is pretty easy. And it's 2 to the 3, and since it's a cube root, I'm going to leave it as 2 to the 3 because I want that cube root and that cube to cancel out. So I have 3 cube root 2 to the 3 y plus 2 cube root y. So I just changed my 8 to be 2 cubed. And I know the cube root of 2 to the 3, those will cancel, giving me just 2, so that comes out. 2 times 3. Cube root y plus 2 cube root y. So I just took the cube root of 2 to the 3 out. And then 2 times 3 is 6. So 6 cube root y plus 2 cube root y. Now they're like terms. They have the same index and they have the same radicand. And so I can add the coefficients and get 8 cube root y. All right, we're doing 11. 11, you're going to multiply the outside times the outside, but there's only one number on the outside, so let's write that number down, 2. 3 times 6 is 18. This is the only x, so leave it x to the 3. And when we multiply the y's, we add exponents. For the 18, I'm going to make a factor tree. So it's 3 squared times 2. I'm going to break the x's and y's into squared pieces. Remember, the squared pieces can come out. So this can become x squared times x to the 1. And this can become y squared, y squared, y squared. So anytime, we did this before, anytime you have variables raised to a power, you can break them into pieces that match your index so that you can use those inverse operations to take them out of the radical. So the things that come out are the 3, the x, and then all of these y's. So I still have this 2 on the outside, times 3, times x, and then y. Square root 2x. And then for my final answer, I'm just going to put everything together. 2 times 3 is 6. X. Y is y to the third. Square root 2x. All right, 13. We're going to distribute the 1 first. 1 times 5 is 5. And then 1 times negative root 2 is negative root 2. So start by distributing the 1. And then you're going to distribute. Root 2 times 5 is 5 root 2. And then root 2 times negative root 2 is negative root 4. All right, so just like we would distribute with any binomials we're multiplying, same deal. First distribute the 1, then distribute the root 2. All right, this negative root 2, or negative root 4, I know the square root of 4 is 2, so that can become just minus 2. These two I can add together, and remember, if you don't have a coefficient on that root 2, you can give it a 1 so that it's easy to add or subtract. I have negative 1 root 2 plus 5 root 2. What's negative 1 plus 5? 4. So that's going to give me 4 root 2. And I still have a 5 here. And then lastly, I'm going to combine the 5 minus 2 to get 3.